Hello. Today we're going to talk about time value and understand the basic concepts of time value. In this particular recording, we will talk about the present and future values of a single cash flow and a series of cash flows, sometimes called an annuity. We'll calculate the return on an investment. We'll use a financial calculator or a spreadsheet, and in fact I will use a spreadsheet to solve some time value problems, and understand perpetuities and annuities. The chapter is outlined as you see here. Let's first talk about the one period case, and we usually start talking about compounding. So suppose you were to invest $10,000 at 5% interest for 1 year. Most people would quickly tell you that you'll have $10,500 at the end of a year. That would be $500 worth of interest and the $10,000 of principal that you started with, making a total of $10,000. And you can, if you add 10,000 times 0.05 plus 10,000 times 1, you get 10,000 times 1.05. The 1.05 is a compounding factor. So this is called a future value. The 10,500 is called a future value. It's what you will have in the future from your investment. In the one period case, the formula, actually that t should just be a 1, but it's the future value is equal to the cash flow at time 0 times 1 plus r to the 1 power, where C0 is the cash flow of the day and r is the appropriate annual interest rate. If you were to be promised 10,000 due in a year, we could kind of go back the other way. So if you're going to receive 10,000 in the future, what would your investment be worth in today's dollars? And to get that, we just do the opposite. Instead of multiplying by the 1.05, we divide by 1.05, giving us $9,523.81. So that's the amount that a borrower would need to set aside today to be able to have that $10,000 in 1 year. And of course, the future value of that $9,523 is $10,000. So in the one period case, the future value, the present value formula can be written, take the cash flow at time 1, divide by 1 plus r. Talk for a minute about net present value, the concept of net present value. Net present value of an investment is the present value of its expected cash flows minus the cost of the investment. So if you had an investment that promised to pay $10,000 in 1 year, and it's offered for sale at $9,500 and your interest rate is 5%, the question is, should you pay the $9,500 for the investment? So we calculate the present value of the cash flow and we subtract the cost, and in this case the net present value is a positive $23.81. You can think of this slide, basically this calculation, as a cost-benefit analysis. The 10,000 divided by 1.05 is the present value of the benefit. The 9,500 is the cost. The difference, if it's positive, means that the benefits exceed the costs. Present value of a cash flow is always, if it's greater than the cost, then the net present value would be positive and the investment should be purchased. And in this case, it's a pretty good deal. In the one period case, we can just write this as present value minus cost, and look at it this way. If you had $9,500 to invest at 5%, you would only earn, if you earn not 5%, you would earn $9,975, but the investment pays you $10,000. So you'd be better off taking the investment than you would putting your money to work for you at 5%. In the multi-period case, we can write the future value equals the cash flow at time 0 times 1 plus r, that quantity, multiplied by itself t times, or to the t power. And of course, C0 is the initial cash flow at time 0, r is the appropriate annual rate, and t is the number of periods or years over which the cash flow is invested. Let's suppose that a stock currently pays a dividend of $1.10, and that dividend is going to grow at 40% a year for the next 5 years. We can apply this formula that we just looked at to figure out what the dividend will be worth in 5 years. So we take the $1.10, which is the cash flow today, multiply by 1 plus R, or 1.4, raised to the 5th power, and we see that the dividend will be $5.92. Notice that the dividend is quite a bit higher than it would be if we just took the interest that we would earn on the dividend in 1 year and kept adding that. So 40% of $1.10 is 44 cents, and if we did that 5 times, we'd have $2.20, and that would only give us $3.30. But we have $5.92. The difference, the reason it's bigger, is because we have compounding. And compounding means we're earning interest on interest, or we're having growth on growth. That's called compounding. Here's a picture, a timeline, and timelines are quite useful, and I suggest to you that whenever you do problems in this class, sitting down, drawing a quick timeline is a good place to start, almost always. Let's just take a look at this. We start out with a dividend that's $1.10, and in the first year it grows 40% up to $1.54. And now here's where we differ, where we deviate from just, notice that we added 40% growth, or 44 cents. This time we're going to earn 40% on the $1.54. And so now we have $2.16. We're now getting growth on growth. And in the third period we get growth on growth and growth on growth on growth and so on. And by the time we get up to the fifth period, we have this $5.92. How much would an investor have to set aside today to have $20,000 5 years from now if the current rate is 15%? This is a present value problem. The $20,000 is a future value. And if we draw a timeline, we see that we have $20,000 out there 5 years from now, and we want to know what that would be worth today. So we apply the present value formula and divide by 1 plus R to the 5th power, and we see that $9,943.53 is what that $20,000 is worth in today's dollars. The next question is, how long would we have to wait? In other words, we want to solve for the n in that equation. And if we deposit $5,000 today in an account that pays 10%, how long does it take us for the money to grow to $10,000? Or in other words, how long does it take to double? Now before I show you the mathematics, because time value problems can always be done in one of 4 ways, and usually all 4 ways. The first is with a formula. The second is with a built-in function, like on an Excel spreadsheet or a financial calculator. And the third is with tables. So let's just take a look here. Let me go back to, let me get a spreadsheet. And the question is, we want to go, and so the function we want here is NPER, number of periods. Now I've put a document on Blackboard called a brief Excel primer, and it basically summarizes all of the time value functions that we're going to use in this class on Excel, and shows you the formula for each one and the syntax, how the function works. But if you start by typing equals NPER and put a parentheses in, all of the arguments that are required for that function will immediately show up. And the first of these is the rate, and I believe the problem said we were going to earn 10%, so I'll put in 0.1. And then the next one says payment, and we have no payment. So you can either put in a 0 like this, or what I prefer to do is just skip it with a comma. And we immediately jump to the third argument, which is present value, and we had 5,000, and then the fourth argument was 10,000. And notice that I've put a sign change in this function. I've put the 5,000 in as negative, and I've put the 10,000 in as positive. You could switch those. You could put the 5,000 in as positive and the 10,000 as negative, and it won't make any difference, but you do have to have a sign change. You have to have some dynamics inside of that parentheses. You have to have something positive and something negative. So when I hit enter, we're going to get something close to 7.27. Now, just an aside here, you may wonder, how did you know it was going to be close to 7? And the answer is the rule of 72. The rule of 72 says that the amount of time it takes for your money to double is equal to 72 divided by the interest rate. In this case, the interest rate was 10%, so 72 divided by 10 is about 7.2. And sure enough, it took about 7.2, 7.3 years for us to double our money. Now back to the slide. We'll see how this works out mathematically. Here's the formula. Let's start by putting the variables in that we do know. We know the future value is 10,000. We know the present value is 5,000. We know that the rate is 10%. And we don't know t. So the problem is to solve for t. Now to get that t out of that exponent, we're going to have to take logarithms. So the first thing we do is the obvious division. We can divide both sides by 5,000. And we get 1.1 to the t power equals 2. The next step is to take logs, and any log base 10, log base 2, log base e. I'm going to take natural log, which is log the base e. And now I can take the log of something to a t power is t times the log of that thing. So you can put the t out in front, and that gives you t times the log of 1.1 equals the log of 2. And then this just becomes a simple division problem. And if you put the numbers in, you'll get 7.27. Let me go back to the spreadsheet for a minute and just show you that. On a spreadsheet, the natural log is just ln. See, it says returns the natural logarithm of a number. And I'm going to put the natural logarithm of 2 divided by the natural logarithm of 1.1. And that should give me 7.27, just like we did. All right. Which rate is enough? Now in this case, we look at the problem again. This time we're going to use this same basic equation. We're going to solve for r. So let's assume that you're going to send your child to college in 12 years. It's going to cost you $50,000, and today you have $5,000. You want to invest your money for this 12 years, $5,000, and come out with $50,000. And the question is, what rate of return will you have to earn? I'm going to go back to my spreadsheet again, and this time the function I'm going to use is called rate, R-A-T-E, and again it says what are the arguments, and the first one is the number of periods, and I'm going to put 12, and the next argument is the payment, and in this case there is no payment. A payment would be a recurring cash flow, and we only have money in, money out. We don't have recurring. A recurring payment would be like a house payment or a student loan payment or car payment or something like that. So we're just going to skip that. The present value in this case is 5,000, and again I do need a sign change. And the future value is going to be 50,000. Now remember not to put the 50,000 in with a comma. You can't put a comma in that. And if I hit the enter now, 21%. Now Excel has a little quirk. What it wants to do is show you interest rates as whole numbers. So if you look at a couple of decimal places, you'll see that the answer is actually 21.15% or 0.2115. Now let's go back to these slides and go through the math. Here's the formula. We put in the numbers we have again. 50,000 equals 5,000 times 1 plus r to the 12th power. This time we know the t, but we don't know the r. So the first thing we do again is the obvious division. 50,000 divided by 5,000 is 10. Now to get the something that's something to a 12th power, what we're going to do is take the 12th root. So we're going to take the 12th root of both sides, and on the left we'll have 1 plus r, and on the right we'll have 10 to the 1/12th power, or the 12th root of 10, and then we'll just subtract 1 from both sides, and we'll have an answer of 0.2115. Okay, and just to show you the mathematics again on the computer, if I take 10 raised to the 1/12, that's the 12th power, and subtract 1, there's the 21.15%. Same thing. All right, let's keep going. I'm going to skip over the calculator keys. This talks about Texas Instruments, Hewlett-Packard is also a common financial calculator. I recommend you use a spreadsheet. If you're going to use a financial calculator, the class is going to be frustrating for you, to say the least, but you can do it. You can do it. Let's talk about multiple cash flows. Here's an investment that pays $200 a year from now, and then cash flows increase by $200 a year. In other words, first year $200, second year $400, third year $600, fourth year $800. The interest rate is 12%, and we want to know what is the present value of this stream of cash flows. I'm going to go back to my spreadsheet. I'm going to get rid of what I have here, and I'm going to put some numbers in here, 1, 2, 3, 4, just to keep track of the time. And I had, at time 1, the end of the first year, I had 200. Then the next year, another 200, so 400, then 600, then 800. Now, one way to do this problem is to apply a formula to each one of these cash flows and then add up the present values. So I can find the present value of the 200. So if I take the 200 and divide by, I believe the interest rate was 1.12, the interest rate was 12, so that's 1 plus R. That'll give me the present value of 200. Now you can use a formula like that. See, I can do that. Oops, I can do that. Or you can use a present value function. Either way. So if I use the present value function, the rate would be 12. And this second one, 400, is 2 periods away. It's not a payment. It is a payment, but it's only a single payment. So I don't put it in as a payment. I put it in as a future value. I'm going to put it in as a negative 400. And in that way, when it comes out, it'll be positive. So there's 318.88. The third one, I'll go back to my formula again, my equation. So I'll take 600 divided by 1.12 to the third power. And the fourth one, I'll go back to my present value function, and I'll put in 0.12 and 4, and the cash flow will be 800. Okay, now I can add those 4 present values together because they are times $0. So basically, if I do this, I can do this. That's legal. $1,432.93. That's what those 4 cash flows are worth. Here's what you can't do. You can never do this legally. You can't say, oh, I'll just add those together and I'll get 2,000. That is not allowed. 200 at time 1 and 400 at time 2 are time $1 and time $2. You can no more add those together than you can add together apples and oranges and horses and cows. You just can't do it. So first we change everything into a constant dollars at a specific point in time, and then we can add them. Okay. Now another shortcut. There's a function on Excel called NPV, not to be confused with the net present value that I talked about earlier. I put in the interest rate, and then I just go highlight this block up here, and I'll get my answer immediately, $1,432.93. So the quick way to do this is with the NPV function. The slow way is to take the present value of each cash flow and then add those together. And either way, you get the same thing. Now let's go through the slides. First of all, we've been offered, this is for sale, this cash flow stream, 200, 400, 600, 800. It's for sale for $1,500, and the question is, should we buy it for $1,500? So if you take the individual cash flows, 200, 400, 600, 800, and add them together, you get the $1,432. So this thing is worth $1,432, and it's for sale for $1,500, and it's kind of a no-brainer. The cost exceeds the benefit, so no, we should not buy it. Another way of saying this is the net present value of this investment is negative. Okay, we'll skip over the calculator version of this whole thing, and let's talk about compounding periods. Now up to this point, we've assumed that interest is compounded once a year. In other words, when interest is compounded, you take the interest up to that point and you add it to the principal. What would happen if we took the interest throughout the year and added it, and then calculated the interest on the balance? So for instance, if we did that twice a year, let me just show you. Let's suppose that, let me get rid of this whole thing again. Let's suppose that you had $100 and you earned 12% on it. In 1 year, you would have $112. Now let's suppose that instead you earned half the interest halfway through the year and the other half at the end of the year. So let's stake 100 and earn just half the interest, or 6%, and that'll be halfway through the year. And then for the second half of the year, we'll earn the other half, but this time not on 100 but on 106. And so what we've done is we've compounded twice a year, and you can see that in effect we've earned 12.36% instead of just 12%. So compounding more than one time a year increases the effective rate. The effective rate of compounding once a year was 12%. The effective rate of compounding twice a year was 12.36%. And if we did 3 times or 4 times or 5 times, the more we compound, the higher the effective rate will be. Here's a formula for finding the future value of a cash lump sum at time 0 if we compound m times a year. So we will take the annual rate, divide by m, and multiply by m times t, where t is the number of years and m is the number of compounding periods per year. Let's look at an example. If you compound $50 for 3 years at 12% compounded semi-annually, what would your investment be? Now first, before I show you that, let me go to the spreadsheet. So $50 for 3 years at 12% compounded semi-annually. I'm going to do this a couple of ways. First, with a formula, I'm going to take 1 plus the interest rate. Now the interest rate in this case was 12%, and we're going to compound it twice a year, so there's the 6-month rate, and we will raise it to the 6th power. That's 2 times 3, 2 compounding periods per year for 3 years, and you see we have $70. Now the other way I'm going to do it is just use the future value, take the rate, which is 12% divided by 2, take the number of periods, which is 6, and take the present value, which is 50. And again, we come up with $70.93. Okay. So there's the equation. Take the 50, multiply by 1 plus the 6-month rate, 1 plus r. R is now a 6-month rate, and we're using the number of 6-month periods, basically. Okay, effective annual rates of interest. A reasonable question would be, what's the effective annual rate on that investment? I've already answered that. The answer is 12.36%, as you can see right here. But let's just go through this. If we take this 50 times 1 plus 0.06 to the 6th power, $70.93, the effective annual rate would be, well, what rate, if we used it once a year, would turn $50 into 70.93? So we can ask this question. If I took 50 times some unknown rate, which I'll call the EAR, and I compounded that rate for 3 years, I want to end up with the same number, 70.93, and I'm just going to solve for EAR. So we're going to divide by 50, take the third root, and subtract 1. And what we're going to end up doing, there's the divide by 50, there's take the third root, and there's subtract 1. We're going to end up with 12.36%. So the effective rate is 12.36%. The effective rate is the annual rate that if compounded once a year will produce the same result as the 6-month compounding produced. Okay. So compounding 12% semi-annually is the same as earning an effective rate of 12.36%. Now, what about this one? A lot of people get credit cards and they offer 18% loan, and it's compounded monthly. What would be the effective annual rate on an APR loan, 18% APR loan compounded monthly? Well, first we find the monthly rate, so we take the 18 divided by 12, we get a rate of 1.5, and then we compound that rate 12 times to get 19.56. So let me do that on a spreadsheet just so you can see it. We'll take 1 plus 18% divided by 12. That'll give us a monthly rate, 1 plus R, where R is a monthly rate. Compound it 12 times and subtract off the 1, and you see we get 19.56%. So the effective rate of compounding monthly, 18% a month, is 19.56. Next time you get that credit card offer and it says 18% APR, realize that they're actually charging you a 19.56% interest rate. All right. By the way, there is a function, and I'm going to caution you not to rely on it, but there is a function called effect, and it goes direct. It allows you to take a nominal rate like 18 and put in 12 compounding periods, and it'll come up with 19.56%. And it'll go, there's another one called nominal. See, if I go nominal and I put in the effective rate and put in 12, it'll go back to the 18. So nominal and effective are kind of reverse functions. But be careful with that. Let's skip over this calculator information and talk about continuous compounding. Question might be, well, we looked at compounding twice a year. We looked at compounding 12 times a year. We could compound 52 times a year weekly. We could compound daily. I suppose we could compound hourly or minute by the minute or by the second. Can we actually compound continuously? Could we actually compound over any period of time, no matter how small? And the answer is yes. And to do that, we take the initial cash flow and multiply by e to the RT, where e is the base of the natural logarithm, and r is the interest rate, and t is the number of years, or the time period. And in this case, 2.718. And I'm going to show you on your calculator how you can do that, or on your spreadsheet. There is a function called EXP. So let me compound 12%. 12% times 1, where 1 is 1 year, minus 1. This will tell us what the effective annual rate is of compounding continuously. And the answer is 12.7497%. So 12.7497 is the biggest interest rate we can get from compounding throughout the period. Okay, some simplifications. The first is a perpetuity. A perpetuity is a constant stream of cash flows that lasts forever. A growing perpetuity is a stream of cash flows that grows at a constant rate forever. An annuity is a stream of constant cash flows that lasts for a fixed period, and a growing annuity is a stream that grows at a constant rate for a fixed period. Let's start with the easiest one of these, a perpetuity. A constant stream that lasts forever, and these three little dots on the right here, these dots right here, signify that this thing goes on forever. There's no end on the right. And each cash flow is the same, C dollars, and it occurs at time 1, time 2, time 3, time 4. And so this is an ordinary perpetuity, ordinary meaning that the first cash flow occurs at time 1. Now these are payments. So to find the present value, we do exactly what we have done in the past. We take the present value of each cash flow, and then we can add the present values together. And the present value of the thing is the sum of the present values. So here's the formula. The first cash flow is 1 period away, so we divide by 1 plus r. The second is 2 periods away, so we divide by 1 plus r squared. The third is 3 periods away. Now mathematically, this thing simplifies, turns out to just the cash flow divided by the rate. So let's look at a simple example. A few years ago, Britain, the British government, sold some Consul bonds. And they're a bond that promises to pay £15 every year forever, or whatever amount they promise to pay, in this example £15. Let's suppose that the interest rate is 10%. What would we be willing to pay for this bond? And the answer is £150. All right, now let's move on to a perpetuity that's actually growing. And the typical example of this is a company that pays dividends. So here's a cash flow of size C at time 1, and then the cash flow grows by some interest rate G, and so it's bigger at time 2 and it's even bigger at time 3. And once again, we find the present value of each of those cash flows and add them together. And in this case, again, miraculously, this big long thing, which goes on forever, turns out to simplify to a very simple thing. Take the first cash flow and divide by R minus G. Let's look at an example. Company expects next year to pay a dividend of $1.30, and then dividends are expected to grow at 5% forever. 10% discount rate, what's the value of this stream of cash flows? So the cash flows, there you see $1.30 1 year from now, and then after that, 130 times 1.05, we grow by 5%, then we grow by another 5, and so on. If we take the first cash flow, which is just $1.30, divide by R minus G, we get a present value of $26. Okay, now let me just show you that on a spreadsheet. It's really very simple. We'll take, I guess I'll clear all this out again so it isn't mudding things up. We'll just take the, let me start out by actually showing you some of the cash flows and how they grow. The first was $1.30, and then each one grows by 5%. So if I just copy these down for a little ways, you can see how they grow, what we're looking at. And these will go on forever, and they get bigger and bigger. And if we go out here for a couple of 100 years, they'll be quite big. But to find the value of these things, we're just going to take the first one and divide by R minus G. And there you have it, $26. By the way, since I have a column of these things, I could use net present value to get an estimate. It won't be a very good estimate because I haven't gone out far enough. But if I just net present value using 10%, and I've already got these cash flows growing, just go out here to the end of this thing where I've only got 26 of an infinite number. So it only comes out to 17. Let me go further down and just show you what I'm talking about, though. I'm just going to copy this down a lot further. Just a lot further. Down a couple 100 years. And you can see now out here in 214 years, I guess, the dividend has grown to $38,449. And if I go back up and find the net present value of this whole thing, it's going to be awfully close to $26. There you go, $26. So what this formula does is value a perpetual stream of these things. Now let's talk about an annuity. An annuity is a constant stream of cash flows, just like a perpetuity, except that it ends at a point in time. And we'll represent that point by T. And we take the cash flows, find the present value of each cash flow, add them together, and that's the present value of the annuity. This thing will simplify. It's not quite as clean as the perpetuity, but it's equal to the present value of a perpetuity times this thing 1 minus 1 over 1 plus r to the t. Now what this is it's the present value of a perpetuity minus the present value of the same perpetuity at time t. So this is a perpetuity minus, I guess you could think of it as a perpetuity minus its own tail, its own perpetual tail. But let's look at an example. You can afford a $400 monthly car payment. How much could you afford if interest rates are 7% on a 36-month loan? So we want to find the present value. Now, you can use a formula, but I'm just going to show you, first of all, let me once again clean this spreadsheet up a little bit. I'm just going to show you that the functions on Excel make it very easy to work this problem. We look at this problem, it says the rate is 7%, and we're using months, so we want a monthly rate, so we'll divide by 12. And we have a 36-month loan. And now we do have a payment, and the payment is $400, and that's all we have. And the answer is $12,954.59. Okay. Now, let me also show you the formula here. If I take 400 and divide by the R, which is 0.07, well, I need parentheses here, 0.07 divided by 12, divide by the monthly rate, you see that I get the value of a perpetuity. Now, if I take that perpetuity and I subtract from it the same thing, only the present value of it, so I'm going to take 1 plus 0.07 divided by 12, and it's out there 36 periods away. So I'm going to subtract the present value of that perpetuity. Oh, and I need one more thing. No, I'm okay. I'm good. Okay. You see I get that $12,954.59. So all I did is I took the present value of that perpetuity, like this. I took the present value of that perpetuity and I subtracted the present value of the same perpetuity discounted 36 periods from now. And that is the formula. And if you go back, I'm going to get rid of that. If you go back, put this stuff into the formula, there you go, $12,954.59. Here's a 4-year annuity that starts 2 years from today. Now, Excel makes this very easy. Let me just show you what we'll do. 1, 2, 3, 4, 5. We'll have a 4-year annuity of 100, and it'll start, we'll just put a 0 in for time 1, and we'll start this thing out here. And I'm just going to use net present value and see what the rate is, 9%, 0.09, and get this whole block of cash flows, and the value is 306.68. Now that was pretty easy. Now let's see what we do with formulas. First thing we do is we move ourselves to time 1, and we look at this thing, and from the point of view of time 1, this is an ordinary annuity, so we can use our annuity formula. We put the numbers into the annuity formula, and we get 323.97. Then we move ourselves to time 0, and we say, well, at time 1 it's worth 323.97, so what's it worth at time 0? So we then use our formula again to bring that amount back to time 0, and we get 297.22. And you know, I think I have a different answer because I used a different rate. But that is useful because it highlights another important idea behind Excel. If you make a mistake, you don't have to redo the whole problem. You can just go in and fix your mistake, like I just did, and you're done. Whereas if I had used a financial calculator, I would have to redo the whole problem every step again. Okay, so 297.22. Now let's look at a growing annuity. Once again, the annuity stops at a specific point in time, and the formula is a little more complicated. It is, once again, essentially, it is the present value of a growing perpetuity minus the present value of that perpetuity t periods from now. The only difference is if we have a perpetuity, a regular perpetuity, it has the same value at every point in time, but a growing perpetuity grows by a rate of g. So the present value at time 1 will be g% bigger than the value at time 0. All right, let me just show you an example. Here's a defined benefit retirement plan, which is a type of pension plan offered by many, by the federal government, many states, and many large companies. It offers to pay $20,000 a year for 40 years, and there is built into it a 3% cost of living adjustment each year. So $20,000 the first year, and then growing at 3%. And if I actually put this, I'm going to get rid of all this stuff. If I actually create 40 years with a spreadsheet, we'll just go down here till we get to 40. Whoops. Okay, there we go. And I put in the 20,000, and I let this thing grow by 3% a year, and all the way down to time 40. These are the actual disbursements that the pension promises to make over my retirement period. And you see the last one is fairly large, $63,340 for the last year. And I want to know what these are worth. And the way I would do this on a spreadsheet, let me get the rate to make sure I got the rate right, 10%. I'd take it net present value at 10%, I've got a comma instead of a period, 10% of that block of numbers right there, and that's it. That's the answer, 265,121. If you use the formula, stick all these numbers in, do the math, there it is, 265,121.57. Okay, now growing annuity, another example. You're evaluating an income-generating property. The rent is to be received at the end of each year. First year's rent is expected to be $8,500, and rent's expected to increase at 70% each year. What is the value over 5 years? To do this with a spreadsheet, pretty easy. I'll take 5 years. I guess it would be handier to put the years here. There we go. And $8,500, and then the rent is going to grow at 7%, I believe, yes, expected increase at 7%. So we'll just let the rent increase by 7% per year. Copy that down. And those are the cash flows, and what we want to know is what are those cash flows worth at time 0 if the discount rate is 12%. So I'm going to say net present value, put in 12%, and highlight that bunch. Now one thing to mention about net present value is it always assumes that the first cash flow is the cash flow at time 1. You cannot put the cash flow, if there is a cash flow at time 0, you can't put it in. You have to add it outside of the function. Another important point about net present value, you can't just leave a space if there are missing cash flows. You actually have to put a 0 in for missing cash flows. Otherwise, it thinks that the next number it sees is the next cash flow. It doesn't understand that spaces are missing cash flows. Anyway, here we go, $34,706.26. We can put this into our formula. Here are the cash flows. We've already done those. There's the 34,706.26. 34,706.26. Okay. What's a firm worth? Conceptually, it ought to be worth its future cash flows. Of course, the real problem in the case of a firm is to figure out what the size, timing of those cash flows is and what an appropriate discount rate is for those cash flows. All right, that sort of summarizes the chapter. I'm going to emphasize what I always tell students. The slides are only an overview, and it's very important that you read the chapter and work some homework problems and spend some time thinking. And when you read the chapter, don't just read the chapter. Take time to look at each individual example and work through it. Make sure you understand where the numbers come from and why the book is doing what it's doing, what the logic is. So quick quiz. How's the future value of a single cash flow computed? Future value, use future value function. How's present value computed? Again, use present value function or divide by 1 plus r to the t. The net present value of an investment is the present value of the benefits minus the costs. EAR is the annual rate that will produce the same result as period compounding throughout the year produces. What's a perpetuity? It's a stream of cash flows that go on forever, and an annuity is a stream of cash flows that ends. And we have both, we have perpetuities and annuities, and we have growing perpetuities and growing annuities. We also have one more category I ought to mention. We do have the category of annuity due and ordinary annuity. An annuity due is an annuity where the first cash flow is at time 0. An ordinary annuity is an annuity where the first cash flow is at time 1, the end of the first period. So an example of an ordinary annuity would be your house payment or your car payment. An example of an annuity due would be your lease, where you owe the first month's rent at the time you sign. All right, that pretty much concludes Chapter 4.